This presentation is about a complete pilot estimation of seismic risk applied to the Greek testbed, Testbed 4 of the European funding project TURNkey, with the long-term task to improve present findings and procedures toward an integrated rapid response system. TURNkey Testbed 4 covers the Achaia prefecture in the southern part of the Western Corinth Gulf, central Greece, one of the most rapidly extending areas in the world. Our risk analysis considers Patras, the third largest city in population in Greece, and the town of Aigion, where notable seismic hazard exists. Patras displays two main fault groups that cross the residential area of the city, a northeast-southwest active fault transcending and a dominant northwest-southeast one. The area of Aigion town comprises a series of segmented west-northwest trending normal faults. This is related to high seismicity located near to both urban centers, with damaging earthquakes of magnitude up to 6.6 from ancient times until recently. We selected the Observatory active normal fault, which extends between the offshore base of Patras and Aigion, for a scenario simulation, as it is not known to have produced a significant earthquake for more than 400 years, thus considering it a major threat to the study area today. The fault length can be up to 25 kilometers and its width up to 12, with slip rate of approximately 6 millimeters per year and recurrence time of 125 years. The stochastic finite fault method that is applied to Observatory's fault approximates the seismic source as a rectangular fault plane of radial rupture that is divided into discrete subfaults, considering to be point sources whose acceleration spectrum depends on source, path propagation, and side effects. The geometry of the selected source model was defined after considering several previous seismotectonic studies. The chosen dimensions define the scenario magnitude, which is 6.1. We currently show an average scenario with homogeneous slip distribution and a hypocenter located to the eastern lower part of the fault model, consistent with the expected nucleation rupture tendency of such an event. The parameters that model the propagation path effect were determined empirically based on representative previous studies in our area. Side effects are incorporated in our model in two alternative approaches, based on a VS30 distribution extracted on a block-by-block level for both Patras City and Aigion town, and on horizontal to vertical spectral ratios of earthquake recordings from the strong crowd motion array deployed in Testbed 4 infrastructures within the context of the TURNkey project. In our first approach, VS30 distribution in the city of Patras is exported from available VS30 measurements at stations locations of the University of Patras and from published collection of such measurements for Greece. The extracted VS30 map is depicted on the left and site categorization according to EC8 on the right. The VS30 values appear mainly in the central and southern coastal part of Patras, indicating stronger soil amplification there. For the Aigion town, VS30 distribution is exported from an available VS30 profile database for Greece and from further VS30 measurements that are included in the corresponding publication for specific sites in the town center. Lower VS30 values appear in the west central part of the town with an expected stronger soil amplification. The synthetic PGE values for bedrock conditions are generated after attributing a mean VS30 value per building block that are then appropriately amplified based on the empirical factors proposed by Pittilakis and Riga 2016 for an earthquake of such magnitude. The corresponding simulation results are shown herein for Patras case. The results for uniform hard rock site conditions are depicted on the left, and on the right when side effects are included. Higher PGE values are found in the northern and coastal part of the Patras city due to the closer proximity to the earthquake source and in line with the derived VS30 distribution. Synthetic PGE values are up to 0.2 G, corresponding to a modified Mercalli intensity up to 7 with an intensity distribution compatible with the acceleration one. Similarly, the results for Aigion, PGE range with a maximum value of 0.1 G, appears to correspond well to the expected distribution regarding proximity to source and site amplification, depending higher distribution in the eastern and northwestern part of the town. Modified Mercalli intensities are also compatible with the PGE distribution reaching the value of 6. For estimating side effects in the simulation based on HVSR, 4 indicative events with medium magnitude were used that occurred close to Testbed 4 and recorded by the available until then TURNkey sensors. 17 sensors were in operation in Patras, consisting of low-cost P-alert and Raspberry Shake sensors and CMG5TD accelerometers, while only one P-alert and 4 Raspberry Shake sensors were in operation in Aigion. The processing of the events recordings for the extraction of HVSR curves was made using the GeoPsy software to the overall duration of events in the frequency range of engineering interest. The average HVSR values from the 4 recorded events are considered for each sensor. Here is an outcome example of HVSR curves as resulted from the indicative selection of 2 Raspberry Shake sensors in Aigion Town and Patras City, in addition to 1 P-alert and 1 CMG5TD sensors in Patras. Simulation results in this case held similar PGA than before, with minimal deviation of expected values. The same applies to the expected intensity curves at both Patras City and Aigion Town. Nevertheless, PGA distribution currently follows more the resulting PGA distribution on Petrec simulation, especially for Aigion Town, implying that more data needs to be integrated into our future analysis from possibly a denser grid of sensor locations. We then proceed to the structural vulnerability estimation in Testbed 4 using the empirical risk UE LM1 approach as it is proposed by Giannaraki and Lagomarsino in 2004. The total vulnerability index of each building is computed from the sum of its attributed typological index and seismic behavior modifiers based on the recognized vulnerability factors that may affect the certain typology. The exposure model in Testbed 4 is based on census data available for analysis on a block-by-block level. Our method concerns reinforced concrete and unreinforced masonry buildings that exist in the city centers of Testbed 4 and can be identified from the census dataset. The considered exposure model in Testbed 4 consists of simple stone, old bricks with reinforced concrete floors, plus the adobe type in Aigion case regarding unreinforced masonry, and 3 types of reinforced concrete buildings without, with moderate, and with high earthquake resistance design, classified in accordance with the evolution of the Greek seismic design codes. Testbed 4 comprises mainly low-rise buildings of both residential and public use, with the majority of them belonging to reinforced concrete of moderate to high earthquake resistance design. Thus, the most probable typological vulnerability index is assigned per building in Testbed 4, with the corresponding empirical scores accounting for seismic behavior modifiers, as it can be deduced from the available description of the census dataset, and after making some considerations for greater safety in the cases where the census description was incomplete. Testbed 4 exhibits mostly moderate structural vulnerability with average total vulnerability index up to 0.6, yielding in general a good condition of the exposed assets. High structural vulnerability in the case of Patras exists mainly in the south-central coastal zone, whereas Aigion Town demonstrates negligible proportion of average vulnerability index above 0.7. This fact can be attributed to the enhancement of the current building stock in the town of Aigion, thanks to rehabilitation after a disastrous earthquake in June 1995, while the remaining vulnerable cases there regard principally abandoned adobe buildings in poor condition. Consequently, seismic risk is defined as a convolution of the derived seismic hazard with structural vulnerability. It is assessed in Testbed 4 per building block by combining the synthetic PGA wavefield as a function of modified Mercalli intensities, including side effects, and the respective structural vulnerability model as a function of the average total vulnerability index. According to the methodology, the mean damage grade is accompanied by the probability of occurrence per EMS 98 damage grades that are perceived as 6 distinct variables depending on the damage pattern ranging from no damage to total collapse. The damage scenario when side effects are considered based on BS30 distribution seems to leave the building stock in Testbed 4 rather intact. Mean damage grades per EMS 98 range from no damage to slight damage in both Patras and Aigion City, corresponding to the maximum probability of occurrence of these damage levels in the overall examined exposed assets. A similar damage distribution prevails in Testbed 4 when taking into account side effects based on HVSR. For the Aigion Town, a single building block presents moderate damage for such an event, while the rest of the building stock displays maximum probability of occurrence up to slight damage level, as this is also the case with Patras City. These results can be attributed to both the estimated PGA range and to the existence of moderate structural vulnerability in the two study areas. In short, the stochastic simulation in testbed 4 for an assumed earthquake of moment magnitude 6.1 on the Observatory fault resulted in compatible synthetic PGA range with both different approaches of including site amplification. Higher PGA are computed in those parts of testbed 4 that have closer proximity to the earthquake source and in accordance with the derived PS30 distribution for soil characterization. Nonetheless, the PGA distribution, when considering HVSR, seems to have low resolution regarding identification of site amplification, especially in the case of Aigion. The exposure model in testbed 4 indicates the existence of moderate structural vulnerability in most parts of both cities, since it consists mostly of low-rise buildings with good structural characteristics. The predicted damage distribution displays an overall satisfactory response of the building stock in testbed 4, with the majority of buildings remaining intact. However, the implementation of a worst-case scenario may modify the current status, as further research is needed regarding other potential dependency factors, such as the investigation of different hypocentral locations with the maximum expected earthquake magnitude from this fault, directionality of source, or incorporation of an heterogeneous slip model during simulation. Additional effects, such as topography that influences the town of Aigion, for example, may be required for a more detailed depiction of side effects, in combination with the analysis of more recordings that will be integrated in the future from the entire accessible network in testbed 4. Thank you for your attention.